We present LitNeRF, a new method of intrinsic radiance decomposition for high-quality view synthesis and relighting of faces. Given a sparse capture setup of 15 cameras and 15 lights, our method is capable of performing novel view synthesis and total relighting of human faces at unprecedented quality. This includes directional relighting, environment map relighting, and near-field relighting. NeRF are the state-of-the-art for novel view synthesis. Thanks to the volumetric rendering, NeRF can capture fuzzy geometry details such as hair and beard. However, they are not relightable in a straightforward way. Furthermore, they require hundreds of multi-view images to train. In contrast to volumetric rendering, mesh-based methods provide full control over the light transport and relighting of a given scene. However, they are limited to surfaces and do not capture complex geometry such as hair, beard, and other thin structures. Moreover, in order to automate learning of the appearance of the underlying mesh model, existing methods use a significantly dense capture system, such as a light stage with 331 lights and 90 cameras for the relightable and neural light transport, and a light stage of 460 lights and 140 cameras for relightable Kodak avatar. These capture setups are challenging to build and therefore are not scalable. In contrast, we use a capture setup that is an order of magnitude of smaller. So how can we retain photorealism of NeRF-like methods while being relightable and, at the same time, use a lightweight capture setup? Inspired by NeRF, we base our method on volumetric rendering to handle fuzzy structures of beard and hair. In addition, we use a proxy geometry to condition and bound the volume to handle data sparsity. To understand our method, let's start by describing the NeRF formulation. NeRF stands for Neural Radiance Fields, and it uses a coordinate-based MLP to represent the radiance of each point and a direction. These radiance values, obtained from the MLP, are then aggregated through standard discretized volume rendering for a given ray to get the final pixel value. The rendered pixels are compared with the ground truth pixels to update the radiance MLP weights. Note that the lighting condition is fixed, and the radiance is computed for the fixed global lighting. However, in the presence of a dataset with different known light conditions, the radiance is dependent on the scene light. We can then rewrite radiance in terms of different components inspired by the intrinsic decomposition from computer graphics. More precisely, for a given known point light, as in the case of OLAT images, we write radiance as an addition of a dominant term of direct component, and a residual low-capacity indirect component. The direct component is then factored into diffuse reflectance, light and view-dependent specular scattering function, light-dependent direct transport function that accounts for self-shadowing and foreshortening. All these components are described by simple MLPs, and the final radiance is computed through the rendering equation. Note that with the known position of the light, we factor out the inverse square distance, making the MLPs normalized and generalizable to near-field relighting. So let's see what our intrinsic decomposition looks like when rendered to a camera. These are the novel views of a subject with a fixed light. And these are the corresponding decompositions. Now we describe how we handle the data sparsity in terms of both number of views and lights. Generally speaking, we leverage a proxy mesh reconstructed through multi-view stereo of the input images. Specifically, we compute a shell by dilating the proxy mesh about 1 cm and use the shell to restrict the volume of the optimization. This reduces the significant amount of floaters during the sparse views, and prevents poor convergence to an all-zero density field due to dark OLAT images. To handle sparsity of lights, we condition the direct light transport function with a precomputed 2D foreshortening rendering on the reconstructed mesh. This greatly helps in generalizing to novel light directions, specifically, in handling the challenging nature of getting smooth shadows. Note that unlike the other intrinsic radiance fields, the direct light transport component that contains the light visibility information is a non-smooth function. Conditioning this function with a precomputed 2D visibility greatly simplifies learning such a complex function. Now we show our results. We start by showing results on the directional light. Note the moving specular highlights in our learned directional scattering function. With directional relighting, our results naturally generalize from our initially captured OLAT conditions to the common rendering scenario where the emitted radiances come from the pixels of an environment map. Also, factoring the distance terms out from the MLPs, our method generalizes to near-field lighting. The examples are shown here. Here, we show an example of near-field relighting and its corresponding decomposition. Note how the intensity of the RGB image changes as the light approaches the subject, but the normalized decomposition remains the same. Now we compare our results with the state-of-the-art relighting methods. Our baselines include the spherical harmonics-based NeRF-SHL method from NeRF, Li and colleagues 2022, in the category of volumetric rendering, and neural light transport, Zhang and colleagues 2022, as a representative method in the category of mesh-based rendering. NeRF-SHL struggles as the light goes through a location, frontal gap, not seen during the training. Neural light transport was originally developed using a dense setup of 320 OLAT images and 80 cameras, also does not work well in the sparse settings. It also shows clear artifacts arising from its mesh-based modeling inaccuracies. While LitNeRF pushes the attainable visual quality of relightable volumetric rendering significantly, it does have some limitations. As we rely on alpha matting for the shell-bounded integration, inaccuracies cause background regions to be included in the model. The indirect chromatic radiance can also present extrapolation artifacts. The disagreements between the conditioning visibility and true visibility in the training data can also lead to double shadows. We argue that both of these artifacts can be mitigated by more accurate proxy mesh and masking methods. To conclude, we verify that it is easy to employ physically based priors on light transport to decompose radiance to diffuse and directional reflectance, direct and indirect light transport fields, all using MLPs. In addition, proxy mesh can be used to regularize the volume and guide the MLPs to compensate for the lack of data. Please see our paper for more details. Thanks for watching.